So welcome back. In our current focus on localization and mapping, we learned how scan matching works and how it serves as a fundamental building block for map-based navigation approaches. Now, assuming you have built a map, we want to estimate the position of the robot as it moves through the map. In this lecture, we will understand particle filters in general, especially particle filters used for Monte Carlo localization. So for localizing the robot in an environment, given that we have a map. As always, this course is a team effort with contributions from a variety of individuals. We're grateful from learning from each other. So here's the lesson plan. First, we'll review how do we start making a map using scan matching. In particular, we will use Hector SLAM. So once we have the map, we'll then explore the particle filter localization approach and specifically one implementation called the adaptive Monte Carlo localization, also known as AMCL. So this will provide us the intuition to understand how it works, why it works. And then we will actually do some analysis into understanding the recursive Bayes filtering used in AMCL and understand the math behind it. And then we'll learn some practical hands-on aspects of tuning these filters in ROS. In a supplemental lecture, you'll have a hands-on tutorial in actually using particle filters for your actual labs. So let's look at the basic path planning example over here. Consider the case of driving through the university building corridors. Now, our car is at the initial position, and the green line represents the path we have to follow. Your path assignments would just involve information of which turn to take, the first turn, second turn, and then so on as a simple sequence, rather than creating a proper trajectory. As we start to race competitively, we will need to follow race lines and take precise turns at maximum possible velocity. As you see in the image, the car should be aware of the paths before and after the turn to choose the optimal path and manipulate its speed accordingly. In several cases, it's not just about optimizing the turn the car can have in the present view. The decision should be smart enough to choose the race lines depending on the next turn as well. As shown in the image here, you have two possible paths, the red and the green path. Both follow the optimal path at the first turn, but the green path is the most efficient one in order to optimize the second turn as well. The path selection is heavily influenced by the remaining track under such scenarios. All of this can be easily achieved if the cars have future track information while making path decisions. Well, even the Formula One drivers are aware of the track before they start the race. Over the next few lectures, we will talk about how we go about mapping the racetrack, make the car smart enough to perceive the surroundings and localize within this track. We will then talk about how to combine both mapping and localization to generate trajectories and then follow them to compete in the next race. To begin with, let's go through the concept of simultaneous localization and mapping, also known as SLAM. And we'll use a particular flavor of SLAM over here called Hector SLAM. SLAM is often considered a chicken-egg problem. You need a map of the environment to determine the robot location, but you need the robot's location first to build the map itself. The way SLAM works is you register your initial map from the first scan and the initial pose estimate. The car then moves by a minor amount in a small time interval. Now we have a new laser scan measurement and an estimate of the car's motion. The current laser scans are then correlated with the map observed till this stage to estimate the change in the position. This way, at each stage, you get a new pose estimate with which we update the map. This process continues over several time samples, updating the map at each step, and this gives us an entire map. We won't go into the loop closure aspects today, but this just shows you a step-by-step manner in doing both the map observation and the localization. So let's see the map being generated by the car. This looks pretty simple, right? So let's delve into it further and analyze it at the implementation level. There are a number of ways in which we could have approached this problem, and there are loads of research articles comparing them. We will talk about an approach centered around the ROS package called Hector SLAM, and you will be using this on your platform. The map we built here is an occupancy grid. As you see in the image, the occupancy grid is nothing but a standard grid where values of each cell indicates if it's occupied, if it's a free cell, or an unexplored cell. The cells where we get confirmed LiDAR hits over several iterations are considered occupied cells, and they build the walls or the occlusions from the map. The cells considered as free cells are the ones where the LiDAR scans had a chance to pass through but did not get blocked or bounced off any obstacles. And the third type obviously corresponds to the cells where the LiDAR scans have never been able to explore anything. Now, when we place the car into this occupancy grid, the LiDAR hits need to be ported to cell values. We maintain a separate database of laser measurements corresponding to each cell value. We consider these measurements as 1 for a coordinate where we have a LiDAR ray endpoint, 0 for coordinates between the endpoints of the car and the car. The cells in this occupancy grid correspond to 1, -1, or 0, depending upon the cell state, whether it's occupied, free, or unexplored. We define a measurement model as a probability of a cell being occupied or free given the LiDAR measurement being 1 or 0, which indicates the estimated uncertainty in the LiDAR data. LiDAR measurements can be pretty accurate. However, you might not want to trust them completely as you may have people moving around while we are mapping the environment. Now, for each given laser scan, the probability values for each cell the LiDAR scan passes through will be less than 1, and hence the accumulated probability would jump quickly to almost 0 and make no sense. To avoid this underflow, we deal with the log probability. You see two equations over here. One corresponds to the log odd probability of occupied cells and the other one for free cells. During each time step, we update the robot pose and map these constants to the particular map cells. This tells us the odds of a particular cell being occupied or free. We keep adding these constants for each cell over iterations after scan of the same region to determine the confidence level of each cell. In robotics, it's a general rule that you deal with unexpected noise sources, and hence you should never be completely certain of your observation. There is always an element of uncertainty, and therefore we have a very probabilistic view of estimation. Now, as we mentioned, we keep adding the constants to the cells to accumulate the confidence level if the cells are free or occupied. To avoid being completely certain, we saturate the cells with an upper and lower limit, so that if updated due to noise or unexpected moving surrounding features, the future measurements can bring it back to the corrected state. Now, when you start building the map, you take the initial pose of the robot as 0, 0 and update the map cells taking in the first laser scan. For example, if this image is a scan, at the initial stage, this is how the map registration will look like. This is our very first scan in this location. The initial map is directly updated by using the log probabilities for occupied and free cells. When the car proceeds a bit further, our goal is to find the pose change with respect to the previous measurement. We do this by finding the transformation between the new laser scan and the previously registered map. We covered scan matching in the previous lecture and will review it briefly in the context of map making over here. As you can see here, we have a scan at time instant t equals t1. The robot moves a small amount and makes a left turn. The laser scans as viewed from the robot frame at time t2 look like the second image on the right. Scan matching will allow us to find the pose change between these two timestamps. and align the scan at the second time instance with the first scan. The change in pose measured with this approach is used to maintain the robot pose while updating the map simultaneously. The laser scans we get are point clouds, which give us information about the 2D map of the current environment around the robot and within its scanning range. Let's see the approach taken by Hector SLAM to find the transform between two consecutive scans. Here, the symbol psi I represents the pose of the robot. The function psi I represents the end coordinates of the ith scan when the pose is psi I. And the function m gives the value of the map cell at the particular scan coordinate. As we noted earlier, the map cells correspond to 1, -1, and 0. Because this correlation is done over occupied cells, we can mask the negative values to 0. The equation here suggests that the term within the brackets is 0 for a point I, where the map cell value, or say the function m, is 1. Thus, when we scan each point, it corresponds to the cell having a value of 1. The summation will result in a 0 value. For a normal case, where we do have certain uncertainties and minor errors, our goal is to minimize this summation. The pose function psi I can also be written as a summation of previous pose and the change in the pose in the small time interval. This now changes the minimization function to a function over change in pose. We expand the equation using the Taylor expansion for function m. Solving it for delta psi I gives us the Gauss-Newton equation for delta psi I, evaluation of which gives us a step change in the pose with respect to the previous timestamp. Now, this operation will give you the change in the pose at each time step. We update the pose with the calculated pose change, transform the current laser scans to the new pose. The map is then updated using the transform laser scans. The video here depicts the way in which you get the LiDAR data in the car's view of the world. The Hector scan matcher will take this data, match the scans between the two timestamps while registering the map, and then update the car pose at each stage. Now, the video here shows the LiDAR scan when it's viewed from the map frame. The change in pose estimated is evaluated at each stage to calculate the new pose, and scans are being aligned to the new pose. The map registered in this video that we just saw would look like this. We observe that once we have the change in pose estimate, we transform the scan to the global frame and then update the global map with these scans. However, the occupancy grid doesn't assign a wall or a free space directly by observing in a single scan, as it might introduce a lot of noise. Observe this video carefully. Apart from the binary occupancy grid visible to us, the algorithm also maintains a value for each cell. This value is a function of the number of times a cell is encountered by the scan as free or occupied, and the probability of scan measurement being correct. Thus, after every few laser scans, when the map is confident of a particular chunk of cells being free or occupied, it gets published as the occupancy map. Now, in this kind of optimization functions, there's a high possibility of getting stuck in local minima. In order to avoid this, rather than using a single occupancy grid, the equation is optimized first over coarser maps to find a pose estimate. The estimate is then used as an input to the optimization function over higher resolution maps. If we provide the resolution of 5 centimeters as the input to Hector SLAM, and we have decided on using 3 multi-resolution grids, the algorithm will iterate over the grids of resolution 20 centimeters, 10 centimeters, and 5 centimeters. The pose update from the 20 centimeter grid will be an input to the process over the 10 centimeter grid, and so on. The map generated here is now a base for further algorithms of localization and planning. It is essential to save this map and be capable of loading it later. The ROS package called map server provides this functionality to save the map and then to load the map using just this ROS run map server and save the map. So coming back to pose updates during Hector SLAM, we get a change in pose during analysis of the laser scan at each timestamp, and thus a source of odometry. Ignoring the map being generated, we can actually use the Hector SLAM package to get a source of odometry information obtained via scan matching. You can also consider using the canonical scan matcher package for the same task. Both these approaches give odometry information. The main difference is Hector SLAM calculates a change in the pose by matching the current LiDAR scan with the map generated during the previous time step, whereas the CSM package or the canonical scan matcher package, as we studied in the previous lecture that's developed by Andrea Sensi, does this by correlating the current scan with the previous scan and not the map. You have seen the TF3 diagram, in previous lectures, haven't you? This is the transform tree for our system once the localization algorithm is implemented. The Hector odometry provides a transform between the odometry frame and the base frame. Now, you will use this package in ROS, and you will come across several parameters. You can go through the website on Hector mapping, a package, to read about them in further detail. The map resolution parameter allows you to specify how fine you want your map to be. The next two allow you to specify the distance or the angle threshold by which the robot should move between consecutive map updates. The default map laser scan set in this package is 30 meters, but the LiDAR you'll be using has a range of 10 meters. The last two parameters are the log odd constants of the occupied and the free cells we talked about during the map update stage. In the SLAM tutorial, we will walk you through installing the package and using the basic launch file for your application. The next section, we will go over the concepts and implementation details of the adaptive Monte Carlo localization and show you how to integrate the map and odometry we generated today for the localization package. In the previous section, you saw how to build a map of the surroundings using Hector SLAM, and also how to use Hector SLAM to obtain a crude odometry of the car. Now that we have built the map we'll go to the next task, is to know where we are in the map accurately. It's crucial to know where we are to decide where we need to go. This helps us plan the trajectory that we should take based on the upcoming corners and also make precise control decisions on the speed and race lines. That way we can decide at what speed we need to approach the corner based on how sharp the turn is and how far we are from the race line. Another piece of crucial information that we need to know is our orientation or heading in the map so that we can decide on the correction to be applied to the steering to take evasive actions against collisions with the wall or obstacles. In general, knowing where you are helps us decide what we need to do next. Hence, we need our car at all times to precisely locate its position and orientation in this map with or without knowing the original initial position. Localization involves estimating the position and orientation of the vehicle collectively called as the pose as it moves and senses through the environment. One way of knowing the position of the car is by tracking from its initial position the amount of distance it has traveled. By measuring the number of rotations of the left and the right wheels using wheel odometry that we saw in the previous lectures, we can calculate the distance traveled from an initial position and predict with some certainty about the car's pose on the map. Here, the green dot is the initial position of the car in the corridor, and as it begins to move, the green path is the trajectory followed by the car as tracked by the wheel odometry. Similarly, even the odometry information from Hector SLAM can be used for tracking. However, both these sources are not accurate sources of pose due to various reasons. First, the method of measurement itself is not accurate. Additionally, as it integrates distance over time, the error keeps accumulating. This causes odometry drift over time. So the longer you run the car, the more inaccurate your position, your pose estimate is. Another problem with wheel encoder-based odometry is that it does not account for wheel slippage, as you can see in the video here, which is very common for high-speed platforms as this one. Due to the high torque of the motors, the wheels spin at the same location before the car starts to move. The odometry believes the car has moved a certain distance, even though the wheel is spinning at the same location, yielding an incorrect pose. Similarly, when even odometry using Hector SLAM suffers some drawbacks. The scan matching based odometry fails when the corridor is very similar, as we have seen previously. Such a corridor with smooth, featureless parallel walls over short distances. In this video, you can see that even though the car is actually moving and recording new scans, which are shown in red, the scan matching based odometry fails to record it because the scans are very similar. And finally, it realizes only when there is a prominently different scan at the end, at the turn of the corridor. Hence, we need a solution that can compensate for the accumulated odometry error, including those errors due to the measurement, wheel slippage, and failure of scan matching. Additionally, we must also be able to localize without providing an accurate initial position. In other words, we must be able to handle inaccuracies in defining the initial pose. One solution is to use Monte Carlo localization, which uses particle filters. Other options to localize are Kalman filters, which use Gaussians to keep track of the position, and Markov localizations, which use histograms. We'll focus on the AMCL-based localization and also further understand how particle filters make this work. To understand about Monte Carlo localization, we first need to see how particle filters work, right? So let's use an example of a robot where we can move in one dimension. The robot just moves, from left to right, or it can move the other direction too. The environment is the corridor with a few doors. The robot can move up and down the corridor. The robot also carries sensors to sense only doors. And so it has this magical sensor that knows, okay, if it's next to a door, here is a door. And has a source of odometry that tells how far it has moved. Initially, the robot has no information on where it is in the map. The graph of the position on the x-axis versus the probability on the y-axis of being there is 0. We call this graph the belief state. It defines the probability of the robot being in that particular position. So we can model the robot's current belief about where it might be by its confusion. This is captured by a uniform function that assigns equal weight to every possible place in this world. This is a state of maximum confusion at this point in time. At the first time step, the robot senses a door. So the probability of receiving this sensor measurement in the corridor is given by a probability P of Z given X, where Z is the sensor measurement, in this case, if it's a door or not, and X is the position. We call this our measurement model, which denotes the sensor reading against position. So all it knows now is that it is located likely next to a door. How would this affect our belief? Well, our belief state is where our robot is in the map, and it has a similar distribution. The measurement of a door transforms our belief function defined over possible locations to a new function that looks pretty much like this. For the 3 locations adjacent to doors, we now have an increased belief of being there, whereas all the other locations have a decreased belief. This is a probability distribution that assigns higher probability for being next to a door, and it's called the posterior belief, where the word posterior means it's after the measurement has been taken. Now, the key aspect of this belief is that we still don't know where exactly we are. And there are 3 possible door locations. And in fact, it might be that the sensors were erroneous and we accidentally saw a door where there is none. So there's still some doubt also about that. So there is still some residual probability of being in these places between the bumps. But the 3 bumps together really express our current best belief of where we are. This representation is absolutely core to probability and to mobile robot localization. At the next time step, the odometry from the robot says it has moved a certain distance forward. So now we update our belief state by moving forward the same distance with some added noise to account for the error in odometry. This is called our motion update of the belief state. This is nothing but our previous belief state that has been updated with odometry information, just shifted. Now, the robot motion is somewhat uncertain, and we can never be certain as to where the robot moved. So these things are a little bit flatter than the guys over there. And we perform a measurement update by reading the data from the sensors. Again, we sensor door, hence our probability of receiving this sensor measurement in the corridor is the same. So this is for the second door. By convolving the measurement update from our sensors with our previous belief state, we get our new belief state, which has a high probability of being near door 2. We end up multiplying our belief, which is now prior to the second measurement, with the red function in the middle. That is the second measurement after the motion update. The outcome has a peak at each door, and the outcome belief looks like the following, right? So there are a couple of minor bumps, but the only real big bump is the one next to the second door. This one corresponds to the second bump in the prior. And it's the only place in this prior that really corresponds to the measurement of a door, whereas all the other places have low prior belief. And it provides very little belief to places far away from these doors. At this point, our robot has localized itself. So getting to the second door and using this convolution helped us localize ourselves. The location where the probability is high is the place where we actually are. This function is really interesting. It's a distribution that focuses most of its weight onto the correct hypothesis of the robot being near the second door. However, practically, this belief state is not used as a continuous function, as that makes it computationally very expensive. It is instead sampled to produce discrete points or positions. Each of these sample positions is called a particle. Hence, we can represent our entire belief state as a discrete set of particle positions of the corridor, each associated with the probability of the robot located at that position. Also, instead of using uniform sampling, where samples or particles are drawn from equal distance apart, we draw particles wherever the probability of the belief state is high. So here, since we have more probability of being near the middle door, the particles are more densely drawn from here compared to other positions where the probability is low. Each of the drawn particles are associated with a weight, which is equal to the probability of the belief state at that location of where the particle is drawn. That is, the particle near the middle door has a high weight, where particles near the other doors have a medium weight, and the particles at all other positions have a low weight. We will look at sampling and how these particles are drawn and how they propagate in more detail as we go further. Now let's look at particles in the 2 dimensions and the process of using them with our race car. Here we will see a map previously generated using Hector mapping. The black pixels of the map denote the walls, and the gray pixels denote all the free space. The red arrow indicates our pose obtained from odometry, which is not accurate. Let's use particle filters to minimize the error and localize more accurately on the map. First, we generate a set of hypotheses of our positions. These are the discrete particles drawn from a Gaussian distribution of mean being our odometry pose with some covariance that defines the size of the region around which we draw the particles from. We end up with a set of poses that are obtained by adding noise to our odometry pose. Then for each particle, we orient the laser scan shown in orange with respect to the particle pose and compute the correlation score. The correlation score S is calculated by using this formula where A is our map and B is our scan. A bar and B bar are the mean values for all the pixel values of the respective maps, where walls have a value of 1 and free space, as we know, has a value of 0. M and N are the X and Y coordinates of the pixels. This equation basically counts the number of black and orange pixels, that's our wall pixels, that are overlapping. We repeat this for each particle and then record the correlation score for each. The particle that aligns well with the map has a high correlation score. So we can walk through particle 1, then 2, and then we see that each particle is a guess with a different orientation and a different position. And finally, we see that particle 6, well, that's pretty good over there, right? And this particle with the maximum weight is chosen as the pose of the robot at the current state. Notice the drift in the pose of the odometry seen in the image to the left is corrected by the particle filter in the image on the right. This might seem minor now, but as we keep driving, the drift will get larger. We repeat this procedure of correlation for each sensor update. First, we propagate each of the particles we generated based on the distance and direction defined by odometry. Then we perform the correlation of each particle as described previously, and then record the correlation scores. The weights of the particles are kept track of by normalizing and multiplying over time steps. The scores at time step t is first normalized by dividing the largest score at time step t and then multiplied with the previous weight of the particles at time step t minus 1. In this way, we can keep track of how well each particle performs and draw more particles from the neighborhood, from that neighborhood, when it's needed. As we are multiplying the weights over iterations, the particles with small weights reduce to a very small value over time, and the particle filter has effectively very few particles to produce good results. This graph shows the particle number along the x-axis and the weights along the y-axis. We can see over iterations, only very few particles become prominent. To avoid this, we resample the particles when the effective particles become too few and reset all of the weights. So we don't want to get into this local minima because that could be a set of wrong guesses that has led us there and gets stuck there. Consider these yellow circles as the initial set of particles that we drew from the distribution. As they propagate over time, their weights change and few particles become very prominent over the others. The size of the blue particles denotes their weight. The larger the size, the larger is the weight. When the size of the blue particles becomes very large, the particles have to be resampled. The resampling is done by drawing more particles close to the particles having the higher weight than those that have a smaller weight. Thus, a new set of yellow particles drawn have a higher density near the position where the particles with the larger weight existed. All the new particles drawn have the same weight, hence the particle filter begins from scratch. The graph is a plot of x and y position of each particle. Each arrow represents a particle in this and its orientation as an arrowhead. The size of the arrowhead is proportional to its weight. The larger the weight becomes, the larger the arrow. So over iterations, as we can see here, few particles become large compared to the others. When this happens, the particles are resampled. We can see that the particles that have more weight are resamples into many small particles very close to it. And very few particles are present far away from that. With this procedure, it is made sure that no particle dominates the distribution and all have a fair chance. Hence, now our particle versus weight graph resamples whenever the particles become very few and starts off with equal weights again. This form of localization is computationally expensive because the need to iteratively calculate the correlation of each particle is costly. So larger the number of particles, more time is taken to localize. In order to optimize this, we use a sampling method called KLD sampling. This technique controls the number of particles based on the difference in odometry and particle-based localization. Initially, when the position is unknown, the particle cloud is large, as we can see in the first figure on the left, due to the uncertainty in the position. But as the car moves, the particles converge and the particle cloud then reduces. Thus, KLD sampling culls redundant particles and improves performance. Now that we saw how the particle filter can be used for localization, let's see how it is implemented in ROS. This is called the adaptive Monte Carlo localization, or commonly known as the AMCL package. The word adaptive refers to the KLD sampling. This package can be used for localizing with laser scans against a pre-existing laser map in 2 dimensions. The Hector odometry provides a transform between the odometry frame and the base frame. The AMCL package provides an other transform to correct for the drift in the Hector odometry to localize accurately in the map. The input parameters are the sensor, that's basically our laser scan, an odometry source, in this case, that's our Hector odometry, and a pre-built map, as you know, that are all the 3 inputs of this package. This package is then going to produce for us a corrected pose of our vehicle and also a particle cloud for debugging. Now let's see the AMCL package in action. Here we are using the map from the previous section. The green arrow is the pose from the odometry, and the blue arrow is the pose that is corrected by our AMCL package. It is a pose of the best particle. The particles are represented by many small red arrows. The difference between the position of the green and the blue arrows depicts the pose correction performed by AMCL. After traveling a certain distance, the error in the odometry becomes visibly evident from the gap between the green and the blue arrows. And this is the car basically racing around the corridor, and that's what you will do in your next labs. Now that we have got the intuition behind particle filters, let's analyze the math of and the algorithms further. Our problem is to estimate the state of the dynamical system, right? And that's the state of the vehicle itself within its environment. In principle, the math and the algorithms behind the particle filter is essentially the same as a recursive base filter. However, there's a particular trick that we use here that makes the estimation in higher dimensional space more feasible. We're going to address the question of how to actually represent the belief of our state in a probabilistic way. Typically, we also want to know how to maximize it, although we won't address that in the lecture today. We will look into how particle filters are an efficient way of representing such a probabilistic belief. In particular, in situations where this belief doesn't look like a bell-shaped curve and is not a Gaussian distribution. So we cannot use a closed form analytical solutions like we use in the Kalman filter. The key principle is to use sampling to estimate such arbitrary distributions to capture discrete approximations of the belief by a so-called set of hypotheses or guesses or particles. Additionally, we are going to use is called a survival of a fittest scheme to concentrate our finite particles to better sample an arbitrary distribution of the belief. This is similar to genetic algorithms or evolutionary strategies where we iteratively use particles to resample based on a cost function. Now, Monte Carlo localization uses a recursive base filter that estimates the posterior distribution of robot poses conditioned on sensor and motion data. Base filters address the problem of estimating a state X of a dynamical system from data or from sensor measurements. For example, in mobile robot localization, the dynamical system is a mobile robot in its environment. The state is the robot pose. The data term includes sensor measurements. Bayes filter assumes that the environment is Markov, which means that the past and future data are conditionally independent if one knows the current state. So we are interested in the belief about the state of our dynamical system, right? This is the posterior distribution of the state given all the actions of the system has carried out and all the observations it has made. So OT are the observations and AT are the actions. The observations could be camera images, distance recorded by LiDARs or ultrasound sensors, basically inputs from whatever sensors you have. The actions of the mobile robot are the motions captured by the odometers, which convert wheel movements into angles per second. And from that, we can actually calculate what action the robot might have carried out. Now, using a couple of mathematical derivations, We won't go into the details here, but I just want to get you to the point of how we can, what is the exact equation that we are working with. So now using applying Bayes theory, a couple of independent assumptions, law of total probability, and another 2 Markov assumptions, we basically end up with this equation at the bottom in yellow. And this is the nice aspect of this equation is that it's actually recursive. So the belief of the robot state at time t depends on the belief at time t minus 1. At the bottom, there are 2 components, right? The first one is the integral, and the second one is the multiplication on the left-hand side. We call this the portion on the left-hand side, the transitional model, where the probability is that you end up in a state xt, given you execute some action u at time t and were at a state xt minus 1 before. So let's dive into this further. One simplification step involves Bayes' rule because we are interested in probabilistic way of representing these actions. So if you carry out an action and I want to actually describe the distribution about where I might end up being as given, I was given in xt before I executed that action. So the Bayes filter rests on the assumption that the future data is independent of the past data given the knowledge of the current state. This is typically referred to as a Markov assumption. So we don't have to consider the entire motion history, just the current state. So what we have here is the approach to estimate the belief of our current state using the previous belief, the transition model or the motion model, and the observation likelihood or the sensor update model. In this form, the belief is a continuous function and does not lend itself directly to a computational solution. So how do we use this in practice for our robot localization? What kind of data structure should we use to represent this belief? So one efficient way is to use a finite set of samples or guesses, and we call them particles, as you now know. So given this map, our goal here is to figure out a good estimate of where we are. And I make a bunch of guesses as to what my pose is, and I want to zone in on what my exact pose is. Traditionally, for state estimation, we use Gaussian filters. The Kalman filter is a popular example used to estimate the probability distribution. The underlying assumption is that this probability distribution is to be Gaussian. So if your underlying distribution is Gaussian, and if your models are not dramatically nonlinear, then the Kalman filter or the EKF is a fine choice. What happens, however, if we have this kind of arbitrary distribution? How can we use a different way of estimating the pose of the robot, if we leave the Gaussian world? That's one of the advantages of particle filter as well, that they are very attractive techniques to do exactly that. So the key idea of the particle filter is not to use a parametric form like a Gaussian, but to use a non-parametric representation of my distribution here. The particle filter uses random samples. So let's say this is my distribution and I generate a set of samples in the beginning. I can see the samples as points which live in my X coordinate, and the more samples I have in a certain area, the higher the probability of that area or that region. I may also assign a weight to the samples. So bigger the oval here, the higher the weight and the higher the probability of the corresponding area. So under the peak, we have large ovals, and the ones at the edges are, where the probability is small, you have small ovals or flatter ones. It's kind of an intuitive way to see the samples. So we represent the posterior by a set of samples, and we see every sample as a state hypothesis, right? So one possible explanation of what the state is, one possible state the system may be in. So I could have 1,000 samples to represent 1,000 possible states the system could be in, right? That's the key idea. So you have areas of large uncertainty, you may need to have a large number, a huge number of samples. So there's no free lunch. You are more flexible with what we have here, because we can represent, any arbitrary function, but this comes at a high computational cost. On the other hand, for a Kalman filter, it basically needs about the same computational resources for varying degrees of uncertainty. So for the state hypothesis X and I typically have an importance weight. So the probability distribution we obtain from this sample set is just a sum over all samples, and the weight of the individual samples and the Dirac distribution centered in the state of the sample. Again, the Dirac distribution is 0 outside the state and infinite at the state, but the integral is 1. So I can use these particles or samples for function approximation. On the left is a Gaussian distribution, and below it is a sample-based representation. The more samples I have, the better approximation will be. And as you can see, the area, at the mode of the curve has more samples concentrated, and then there are less samples towards the tail of the Gaussian. On the right, you have this fancy distribution where the peaks have high concentrations of samples and the smaller concentration at the dips. So more samples, I have better approximation. And the question is, how do we obtain these samples, and how can we actually generate those samples? And that can be, a little tricky. So if my state estimation is a Gaussian distribution, I can use this closed form, term is to just take 12 random numbers between minus and plus the standard deviation of the Gaussian distribution, sum all of them up and divide by 2. This generates samples from a Gaussian distribution that's centered around 0 with a standard deviation. So for certain distributions like a Gaussian, I can efficiently generate these samples, right? But the question is, what about other distributions that cannot be represented by this kind of closed form equation? How do we generate samples for those distributions? One technique relies on the importance sampling principle. Let's say we have a function f, which is also called the target distribution, right? So that's in blue over here. We want to generate samples from this target distribution. Unfortunately, this distribution has some form where we cannot generate samples from in a closed form. The important sampling principle tells us that we can use a different distribution, which is called G, or the proposal distribution, or sometimes called pi later on. And we can actually generate samples from this other distribution from the proposal. Let's say we take a Gaussian as a proposal, which is different from what the target is. Obviously, you can see that between the Gaussian in red and our target distribution in blue. So we have our proposal in red, right? And we have selected the Gaussian as our proposal. So we generate samples from this proposal distribution, and then we do a correction taking into account the difference between the target distribution and the proposal distribution. This introduces the weights called the local importance weights. And this is given by evaluating the value of the target at the sample location divided by the proposal distribution. And that gives me the weight. So if I have my proposal distribution in red and my target distribution in blue, I generate samples from this Gaussian distribution. So the spacing in X, the location X, drawn from the Gaussian distribution, but then the weight of the sample is the difference between these two distributions. So as we can see here, I can have a large weight when the difference is large and a small weight when the difference is small. So if there's a big difference, I get a large weight depending on the ratio. And so a large or small weight in this way corrects the samples, and I obtain samples which follow my target distribution. That's what the importance sampling principle tells us. What the particle filter now does is it uses the samples to represent the posterior and uses exactly the importance sampling principle to update the belief. So it's a recursive based filter, and specifically a non-parametric recursive based filter. That means we do not maintain a closed form distribution like a Gaussian for the target distribution. We take those random samples as my representation of the underlying distribution, and I update my samples based on the motions that I have and based on the observations that I obtain. It does this in two steps, a prediction step and a correction step. The prediction step draws samples from the proposal distribution. That's a distribution I can easily sample from. In terms of localization, I typically use my motion odometry as my proposal to generate new samples taking into account the motion of the platform. And then I take my observations for doing the correction. That's my LiDAR scan. Therefore, if we do this, we see the connection between the prediction and the correction step. The important thing is more samples, obviously we have better estimate. The particle filter has three main steps now. First, it samples the proposal distribution. This is where it generates the samples from my proposal. This is a distribution which I choose as a designer and from which I can sample efficiently. And let's say for the sake of argument, I choose a Gaussian distribution here because that's efficient to sample from. Then we compute the importance weight, which takes into account the function that I actually want to approximate. The only thing I require here is that I can evaluate point to point wise, right? So for every point in space, I can evaluate this value and divide it by the proposal. This does the correction, telling me what's the difference between the proposal that I chose to generate samples from and the function that I want to approximate. It's kind of a correction for the fact that I actually sampled the wrong distribution, right? The third step is a so-called resampling step, and it's kind of sampling with replacement. So I have my weighted sample step after step 3, and then I just draw J samples out of that with replacement. The probability of drawing a sample is proportional to the importance weight. You can see this informally speaking as a kind of survival of the fittest. It's quite likely to pick a sample with a high weight where the approximation was good. And I eliminate these samples which haven't been drawn. So those are more likely to have a small weight and they essentially just die out. This way I focus my sample set on the likely part of the state space. So let's look at how this is captured in the particle filter algorithm. As inputs, I have my old sample set, that is the previous belief over here as xt, and my controls and my observations, right? So the same input as a base filter. Now we initialize two new sets, the predicted set and the correction set step. The two new sets over here, and we initialize, and they both start as empty sets. I iterate over all my samples in my previous belief, and I obtain a new sample for J by sampling from my proposal distribution. In practice for localization, I take the sample out of my previous belief, apply a motion forward, and then sample around that area. For every sample, I compute the correction by taking the target distribution divided by the proposal, and I add that to my predicted sample set. This is what I do for all the samples in this loop. Next, what we see down here as a resampling step. So we draw a particle that's proportional to its weight, and I include it into my resulting sampling set. This is what we return. Let's look specifically into Monte Carlo localization, which is a specific instance of particle filtering. So for each particle is a pose hypothesis of the robot. So it has an X, Y, theta state of the system that I may be in. Typically in Monte Carlo localization, for the proposal distribution, we choose the motion model. So how does the robot's motion, UT change the state? We take every sample out of my previous sample set and apply my motion model and move it and sample from that model. This generates the next generation of those samples. And then I do the correction step. The correction step takes the value of my target distribution, divides it by my proposal. So my odometry, that's my odometry. This way we obtain this correction. So that's exactly my observation model. And I'm getting a better and better fit now. So if you use the motion model as your proposal, that's your final observation model that you're going to obtain. So we can derive the particle filter algorithm for localization in exactly the same algorithm that we had before, except we changed the two lines which are underlined in red, in which my odometry model, motion model, odometry motion model as which I sample, and the observation model for doing the correction, right? So I'm using my motion model and I'm using my observation model for the correction step. So what we see now in this example here are samples, spread all over the place at the initial point in time, right? So all the red dots are samples, as that's one possible pose where the robot may be at the moment. In reality, the robot was starting at the center, in this purple dashed line that you see here, and moving across the corridor and then going to a room on the top. In the top right over here, you see the green dot illustrates the initial best estimate. In the beginning, the location is random because it's just one random particle, as it might have some weight, right? So these blue lines are kind of the sonar readings of the robot that actually is perceiving this world with its sonar scans. And what we see right now is a sequence of prediction and correction steps and resampling steps that evolve this state. So we propagate all samples forward according to the motion of the robot, we weigh them, and then we do the resampling step. With each resampling step, the bad prediction particles are more likely to die out, and the good particles are more likely to survive. After a few steps, the system identifies a road, must be the corridor, because that's the area which best aligns with the observation. Then we see something very interesting happening over here. We have two states because the corridor is quite symmetric. So there is no way to figure out which one is better until it goes into the room and you can say, okay, the observations fit this room and not that room over there. And so those samples die out from the room at the bottom, and the other samples set from the room at the top survive. That's the kind of nice thing over here, because during the estimation position, we can have multimodal distributions, right? I mean, we could be in any of these rooms or in either of these two rooms, or we could be here or there, right? We can't be here and there, but we are trying to zone in on where we are. And only until you have seen enough information about, say, that specific room, you can actually tell, where you are in reality. That's a strong advantage of this particle filtering technique compared to things like, Kalman filtering, which only has a single mode. In the resampling step, we have our sample set with the weighted sample, weighted sample set. And then I just pick out n samples. I draw n samples with replacement, and the likelihood of drawing a sample is proportional to the weight. Why do I do a thing in the first place? And because I have a finite set of samples, and with a finite set of samples, you want to concentrate those samples in the region of the state space which substantially, have a higher probability versus where they have a lower probability. And so if we happen to have an infinite number of samples, we don't care if a large number of samples is going to an unlikely region, as long as we have enough samples in the areas with high likelihood. But for all practical applications, we only have a finite set of samples that we represent, kind of on our computer. And so we do, as we let the bad ones die out and use the samples, to actually represent samples of the higher likelihood areas. So this kind of trick, avoids what you have is a lot of samples that are basically in zero probability areas. In practice, this resampling step is actually essential. So if you don't do this resampling step, you won't be able to track the pose of the system over long periods of time, because your filter will simply diverge. You won't have any samples, which represent the likely areas. So here's a final example, putting it all together. The demo actually is over 20 years old, from Carnegie Mellon, when the researchers were at Carnegie Mellon here. And this is actually an example of when Monte Carlo localization was first developed. So this is a museum in Washington, DC, and what we see is the top view, and we want to localize the robot in this world frame. The robot has two laser range scanners, one looking to the front and one looking to the back. And basically this gives us our first observation. I think there are over 10,000 particles, at the initial stage. And then we do a resampling step and then a motion update. And then we take another measurement, and then the weight is updated. The resampling is done. You can see how the particles have died out now. And then the motion update is performed. So you can see from here that the motion update introduces some noise because there's some increased uncertainty, and therefore the particles are spread out. And this comes from the sampling procedure. And then again, you take a measurement and do a weight update. So you see the samples are a lot darker in the areas of higher probability where the robot is. And then you do resampling and the unlikely, states die out and it starts to concentrate. So in just a very few iterations, we're able to get a really good, estimation of where our robot is. And you can actually continue this process and continue to localize the robot. So this technique is called a Monte Carlo localization. And that's basically the gold standard for localization, today. So we'll end with some practical ways of understanding the actual implementation of the particle filter. We touched on this briefly before. So obviously, the one parameter that's really important is the number of particles. Now you can imagine if you have 10,000 particles, you would have to simulate possible range vectors of 10,000 times, and then each of them would have thousands of rays. So it's heavy on computation. You also don't need to simulate all 1080 LiDAR measurements from the discrete ray casting. Perhaps you can downsample by a factor of 4 or do the same for even the angle step. The range of the LiDAR also influences your particle filter, because the longer you can see, the better shot you have about getting those unique correlations right, from the beginning, right? So if you have a 30-meter LiDAR, in general, you start to localize much faster, and also you maintain that estimate throughout. Furthermore, you can get rid of the useless LiDAR measurements with no returns, or those hitting the floor that don't help you in the update step. So the particle filter can be set up actually to run in parallel on the GPU, as matrix multiplication is very compatible with running in parallel. And that elevates a good deal of the compute concerns using the particle filter. To run the particle filter or AMCL, you have to give it a map file in our launch files. So we send the path through the map server, and this map has to be a 2D cost map. In the launch file of the particle filter algorithm, you need to list where your map is. Then this will open your RViz, where you can specify your initial guess, and then it will spawn the filters to estimate the position of the robot in the map as it moves about. Some important parameters in the AMCL package, allows you to tune are the min and max particle cloud size that KLD sampling must adhere to. Making it too high can reduce the update rate, and reducing it to few particles will affect the localization accuracy. Minimum distance and angle update parameters that we discussed before, decide how frequent, to publish the corrected odometric drift. So as you're moving, again, making it too small, provides bad localization due to insufficient samples. The initial pose gives the ability to programmatically define the starting position of the car, and this can also be set manually, through RViz. Finally, the covariance of the Gaussian distribution can also be set. This defines the spread of the particles around the mean position. So to sum up particle filters, so what are particles? They are recursive base filter, and especially a non-parametric variant. This means that we don't have a parametric distribution with which we can describe our posterior, but we use random samples to do that. We draw the samples from a so-called proposal distribution to advance to the next state, and then we do a correction in order to take into account the proposal distribution was not the target distribution that I'm trying to approximate. And then the final step is a resampling step, and this is a technique which works very well, especially in low dimensional spaces. So for higher dimensions of the state space, more samples are needed, and then eventually, it would get intractable, but particle filters are still extremely scalable today. So Monte Carlo localization is a product, of a special instance of doing localization with the particle filter. It uses particles to represent the pose of the robot in terms of the XYZ position and the orientation theta. It uses the motion model typically as a proposal distribution, and the result of this, is a choice of this importance weight, as we just discussed, is corrected with the observation likelihood. Right? So Monte Carlo localization is the standard choice for localization today. There are lots of additional resources that are listed here. In fact, I highly recommend you actually look at this awesome free book. A lot of the material from this lecture was taken from this probabilistic robotics book. And we will also follow through with a hands-on tutorial after this. And thank you.